I'm a senior director in the data center engineering group at Intel. This is Andres, and he's a senior PE. I don't think they can see you, the camera's here. He's a senior PE in the cloud group, and is an expert on AI and helps drive our strategy. So we'll get into it. Okay. So just before we, just wanted to level set a little bit on what are the different deep learning trends and what we'll be talking about. So in general, if you've worked in deep learning or read any articles about it, there are two main workloads: training and inference. As Ian pointed out earlier today, I mean, we do a lot of training as well, Xeon-based training. But for the purposes of this discussion, we'll be focused mainly on inference because the instruction that we have optimized is for inference. And the data precision has been something that has been evolving over time. So floating point 32 is where we all started. And we've kind of been like sifting through the data types. So it's been FP16, then int16, then int8, and then I've heard int4 now. So we have been, doing that. But in general, the data precisions that we'll be talking about today are floating point 32 and int8. And bfloat16, as Ian said, is also something that we are looking at for upcoming platforms. The other trends in general that we've been watching as a company and also helping, working towards integrating, coming up with those instructions is all the new use cases. When things first started for deep learning, it was all about image classification and convolutional neural networks, which is where we started, was like the ResNet 50 and so many different variants of it. But now we've had definitely a lot more focus and a lot more emphasis on like recommendation systems, language translation, and all of that as well. And of course, going forward, reinforcement learning and other aspects. So that's kind of the trends that we've been watching, and a lot of our processor support is based on those. And of course, the different frameworks we'll be talking about it as we go through it. Different frameworks that we optimize with TensorFlow, MXNet, PyTorch, and all of that. So this is. So I wanted to, before I get into the details, I wanted to get into, show you a brief demo of, stepping through, walking through a brief history of the optimizations that we've done since we launched Xeon Scalable, the first gen Xeon Scalable. Since Ian already did marketing, I think we'll just get back to calling it Skylake and Cascade Lake. So Skylake is what, we launched last year in July 2017. And then now to where we are today with the second gen Xeon Scalable with DL Boost, okay? And so what this demo will do is basically show you how much performance optimizations we've done for a popular image recognition workload. So as you know, the internet is all about identifying how quickly you can identify different varieties of cats. This demo is not just to make it visually interesting. We have other images as well, not just cats. Because Xeon can identify cats all day really fast. So, okay, so on the left you have where the performance of Xeon Scalable at launch, and on the right what we did with just software optimizations from July 2017 when we launched it. So there was like a 5.7x improvement in speed up when we started, and then now with DL Boost, with the baseline, we're able to get like a 14x improvement in speed up. And so if you see the difference, so basically it's how quickly we're inferring. You should be able to see it in the demo. And it's a real, it's not just PowerPoint. This is a real, just a video of a real demo that we took. And of course, when we now since it's never a good idea, since it's like you can never get good performance, for identifying cats fast enough. We actually had like the Xeon Platinum, the 9200 series, which actually doubles the performance, more than doubles what we get with the 14x with DL Boost. So that's actually a 30x improvement in performance. So if you see the demo ended, but if you see like the range in which we've been doing the optimizations, so 1x is when we launched, and 5.7 is just software optimizations and hardware tuning and all that. On top of that, for a first gen Xeon Scalable, 14x is what we have today with DL Boost, and 30x is what we have, again, with the 9200 series with DL Boost.
If I can make another comment.
Yes.
So when we launch Skylake, this is the baseline. However, this is already with a bunch of optimizations that we had done. So if you were to compare when we launched Skylake, the software optimized versus unoptimized, there was a 50x improvement. So this is already with Intel's optimizations. Then we did more optimization, the performance got better. But without any optimizations, the performance really poor. And so this created this notion that Xeons were not a good platform for deep learning workloads because the software was not supporting that. And this is something I'm really proud of Intel, where we have come from having 1/50th this performance all the way to where we are today, in large degree through software optimizations and this boost through the hardware features in Cascade Lake.
Yep. All right.
Can I ask you, so if I compare this feature with a GPU, okay, I don't even know if...
we'll talk about it.
No.
Are you going to talk about I think your question is, how does it compare?
Yes.
We'll talk about it. So this is based, so how did we do the magic that we did, right? So this is the solution stack of what, and Ian talked about a little bit, of all the components that are needed to integrate this. So at the base, of course, we have our Xeon Scalable Processor with DL Boost, and then we have like bunch of workloads on top. So basically, I mean, Intel is leading the ecosystem to drive Intel adoption for inference on CPUs. So to get to this, there was actually, and some of you had asked this question before with FP32 and Int8 and all of that. So to get to that, there was extensive pathfinding and industry research that we had to do to get to that level of precision from FP32 to Int8 with minimal accuracy loss. And so for some of the customer workloads like healthcare, video analysis, medical imaging, et cetera, that we'll be talking about, maintaining accuracy is as important as delivering performance. And then the second part is, which Andres touched upon, is our deep expertise in solutions engineering actually is what helps us get to that end-to-end stack. And it's not just about, like tuning just inference or tuning one part of the workload, right? Because a workload is part of a larger stream of an actual use case. And so you actually need experts across the company. I mean, we have about 10,000 engineers across the company, software engineers that help us tune different workloads depending on what the use case is. And then we, of course, drive these optimizations into several open source frameworks, as you know, TensorFlow from Google, PyTorch by Facebook, MXNet from Amazon, our own OpenVINO toolkit, Paddle from Baidu, etc. And then the most important component of all is Intel MKL libraries, DNN libraries. So these are open source libraries that we provide to our developers and the vast ecosystem that actually provides deep learning primitives. So it was providing FP32 before and DL Boost now, that helps the developers and the vast ecosystem actually have a turnkey acceleration solution that they can use to integrate the full stack. So now that we've shown you all the ingredients, I'm going to let's see how these come together. And so I still haven't got to the GPU slide yet, but this is basically a lot of conversations in deep learning have been about image classification. While that's an important workload, Intel has been busy optimizing a whole range of workloads as well that are important to our customers. And so this slide is actually gives you, I mean, is an example of the breadth of workloads that we've optimized for DL Boost. So if you start from and across all these different frameworks and across all these different use cases as well. So you start from the left, the baseline here is optimized Skylake FP32. So not the one at launch, but the one that was, the optimized version. And then the bars represent about, all the different, the 2 to 3x performance improvements that we are getting across the different workloads with minimal accuracy loss. So accuracy loss is important, as I was saying, because as we're going from this lower precision, right, from FP32 to Int8, maintaining the accuracy of the inference is very important. So it's no good trying to, identify an image 2x faster if you've identified it as a dog instead of a cat. So some of our customers were actually pretty surprised to see the level of accuracy, loss that we've been getting. So if you see the industry standard for Int8 is about 1%, and so we're actually getting 0.5 and some negligible accuracy loss in some cases. So that actually is a true testament of the quality of the hardware and software optimizations that we've done with DLBoost. So, if you see, and the other thing why, this is just numbers on a chart, but if you look at the type of workloads, as Ian was saying, not everything is like a pretty nice matrix that can be used like for a CNN. The reason why Xeon is the general purpose nature of it is it's one size doesn't, one accelerator or one ASIC cannot solve all these workloads. You need a separate ASIC for each one of these workloads because of the way the matrix sizes are. So some of them actually will not do very well with SIMD instructions that, and parallelize across GPU cores. So that is the reason, so that's one of the, I would say, a big advantages of actually having a general purpose compute like Xeon, where you're able to do the inference, but at the same time do something else as well.
So all these models have been optimized for Int8 then?
Yes.
Is that
Correct.
hand optimized layer by layer kinds of things? Is that how this works?
Right. So some of them are hand optimized. It depends on, and sometimes we have quantization tools that we use to, like, when we get to a methodology for one set of models, then we use those tools and apply the same methodology for the other. So that's how we scale. So for something new, we'll do the hand optimizations and actual, tuning. But then, like, we scale with tools.
And to add to what Niv is saying, we take these models and examine the layers of these models. And for each layer, we implement the specific layer, both at FP32 optimized and also a different optimization kernel at Int8. And we incorporate both of these optimizations into the Intel MKL DNA library. And these optimizations are for a particular type of layer. So for example, you might have like a convolution layer.
Right.
We might optimize for various sizes of
Recurrent
convolutions.
network, things of that nature.
Yeah, that's right.
And so pretty much everything is available online, available publicly, either upstreamed or staged as PRs in the public domain. So you should be able to, if you're interested, get the config details and all of that and actually reproduce these numbers and try it out. Okay, so now I want to get into the comparisons that we talked about. So, we've been talking about like recommender systems and different types of workloads that we've been looking at, right? So we want to deep dive into one such workload that's actually very important to the cloud. So recommender systems represent about 60% approximately of AI inference in the cloud. As you know, that about I think 80-90% of inference in the cloud runs on Xeon. And a big part of that is also the Xeon affinity for some of the workloads that run in the data center. You've all used, everyone's used recommendation systems. It's what Amazon could be using for recommending products to us, Netflix for movies and shows, Facebook for ads, Google for search, etc. So this example here shows comparison of a wide and deep, which is an example recommender system that we used on MXNet, which is Amazon's deep learning framework, for a batch size of 512, which is a typical production batch size that's used in cloud service used by cloud service providers. Again, comparing that with the NVIDIA V100, which is their high-end GPU in the data center. So we have the FP32 results, and then we have the comparison of our FP32 results for the two-socket Xeon.
Isn't it the T4 now, their GPU? They recently...
They do. They have the T4s as well.
T4, yeah.
Yes. And
which is 2 times faster or 3 times faster than the previous release. So you are comparing the latest CPU with
Yes.
an old GPU.
So-
they have the T4 now.
So yes, but they don't have a high-end GPU yet. So the V100 is their last high-end GPU that they've released.
I don't know.
The
I see on
T4
their
is a low
website
power
the
inference
T4.
chip. The T4 is a low power inference chip. It's not
Okay.
that high-end. So it's
Okay.
like the 75-watt part versus like, I mean, you know, whereas a 2-socket Xeon is, you know, so in TDP it doesn't match. Yeah.
Okay.
But I mean, we have performance numbers with T4 as well that we've shown, where we're actually beating the performance of T4. So the V100 is the higher part. So,
Okay.
yeah. Okay, and the other interesting thing to note here is with Int8. So of course we were getting about a 2.4x improvement in performance with just the FP32. NVIDIA hasn't published Int8 numbers for this workload, and so we have actually so we were not able to, so that's why it was an apples to apples comparison with FP32, but we have even higher boost with Int8. Okay, so now I want to get into some flavor of the customer engagements that we've done. So we have a wide range of customers that we've been working with, like giving them early samples and working with them to on different use cases. So give you a flavor of like different partners that we work with. I think if you were at launch today, so Lisa had Siemens on stage talking about the medical imaging that they did and how DL Boost has been improving their performance. So Siemens Healthineers is actually a global market leader in diagnostic imaging, and this has been what they've done. Their solution with DL Boost in combination with OpenVINO, which is our deep learning toolkit, actually improves performance about 5.5x over like existing infrastructure. And what's interesting about that quote here is, and this is another reason why, I mean, they've been, they actually do not see a need for a discrete GPU investment because of the performance gains that they are seeing with the second gen Xeon. So that's an example, and then I think they had a really nice demo. My slide doesn't do justice to it on how the cardiac MRI and was able to detect anomalies in the heart much faster now than they had before. So that's one example. So another example is from JD.com. So they actually, this is for a text detection use case, and the challenge here is to achieve, so it's not just about performance, but also like achieving real-time latency. And so their use case was about, how quickly are they able to, find text areas in a video or in an image. And they were able to use DL Boost and get quite a good performance, get about 2.4x improvement in performance than what they had before. And so this is the other like part of DL Boost, which we have a lot of our other customers corroborating us with this with us as well. Is like the TCO story is definitely something that they are able to take advantage of. And so, like as I was saying before, TCO math is complicated between like different companies and what they do. It's a trade secret. They don't talk much about it. But in general, with like the assumptions that we've got from our customers, we're able to see that there are benefits, and their JD.com in this case is corroborating that as well.
2.4% faster than what they had.
Than what they had.
What was what they had?
What they had was like was actually like a first gen Xeon scalable.
So it was still Intel.
Yeah, it was still Intel. Yes, and some of these, a lot of these companies are also constantly looking at accelerator investments and what to do when they come up with new use cases, right? Sure. So the fact that we're able to do the built-in acceleration, and then all they have to do is do a refresh, a Xeon refresh, and be able to support that workload as well helps a lot. And so that's why, I mean, when they say TCO and all that's part of that they don't have to invest in an accelerator, and they're able to just do this with Xeon. Okay, and so the last case study here is basically on an ISV case study on face recognition and medical imaging. So this again is some customers in China. So Asia Info and Hisign did a face recognition study with like they've been ISVs helping us with e-commerce and e-passports and all that for a period of time. They again their challenge was to get real-time latency, and they were able to get that with actually going from FP32 to Int8. And I think in these cases they actually had a much older version of Xeon, and they were able to still get a 2x improvement in performance, and the same thing with NewSoft as well. And these are actual proof points that have been deployed at the customer sites as well.
Do you know if this is all in-house or part remote, part in-house, or?
Some of them were in-house, but some were actually working with customers, because these are ISVs. They sell to customers, like end users directly. So some of them are actually with end users.
Oh, I meant the performance, as in, was everything performed in-house to get the recognition going, or did they try something over a longer wire?
They did.
Okay.
So they were doing it over the wire.
Okay.
Okay.
Yes.
What's more important or interesting, I think, to me is comparisons, not to the precursing Xeon processor, but to what's current on NVIDIA. And maybe I'm biased. I have a customer who's doing a fairly significant project, and I'd like to help them with the new architecture, should it be appropriate. Do we have any good?
We do. So a lot of, so as I was saying, it depends on the workload.
Of course.
So for workloads that have so we think that, like what we call the non-CNN workloads, like recommender systems, recurrent neural networks, language translation, those type of workloads have a better affinity for Xeon. Like a general purpose, CPU compute, like where you don't need to, where you're not able to parallelize across different GPU cores. So those type of workloads run better. And so some of the results that we have actually are able to, show that when we compare that with like a T4 or a V100 or, any of the high-end cards as well. But like for image recognition and classic workloads where we have, where a GPU, where you need that SIMD parallel instructions, we are in the ballpark of the access. So that's kind of the message of what we're having with DL Boost, right? An accelerator is definitely going to be better than a general purpose compute in general.
Oh, of course.
But with the optimizations that we are doing right now, we are getting accelerator-like performance for a lot of the workloads. And that's when, you have your other trade-offs that you're talking about.
And we're not talking about the new Intel-based GPU yet.
Yes, and we're not, right. Yes. Yeah, we're still talking about, Xeon with DL Boost.
Excellent.
Yes.
I'd like to address a question that was brought up earlier. Somebody asked if you could use DL Boost for training. And the quick answer was no, but I just wanted to explain why not. And the reason is for training workloads, it often requires much higher precision than 8 bits. There are some projects in academia that show that for some workloads, you can use 8 bits for training, but those workloads are not production level workloads, they are academic research. If in the future, that type of workloads moves into production, then this instruction can be used for training, because instruction is just a MAC. It's a fuse, multiply, and add instruction that currently is benefiting inference because inference works decently with 8 bits, but in the future could be used for training. And in that case, we would enable the software stack to support it. But just algorithmically, in production level workloads do not work with 8 bits for training. The other thing I wanted to point out is somebody asked, well, are Xeons really used for training? And there is a number of companies that have been public about, hey, we're using Xeons for training. Facebook published a paper detailing the data center usages. They said that all their inference happens on Xeon. And also, during the off-peak cycles, sorry, let me replace it. All their inference happens on Xeon, and the training happens in both GPUs and CPUs. There are some workloads that have an affinity for Xeon, and they train those workloads on Xeon. But in addition, they use their spare capacity during the off-peaks. During the diurnal cycles, they have a lot of spare Xeons that they also use for training. Baidu has been very public as well about regarding training and inference on Xeon processors. I cannot think of the top of my head who's been public and who's talked to us in confidence, but those two I know for sure that have been very public about training, not just inference, but also training.
So then DL Boost effectively runs with any framework that's out there today. You could have, if you've got the right processor, you could run DL Boost.
So not with any framework, but with the popular frameworks.
Oh, just the popular framework.
So it runs with TensorFlow,
right? Yeah.
It runs with MXNet, it runs with PyTorch, and it runs with
Paddle.
Paddle.
I mean, so
And our version of Caffe. So we have a Caffe branch, but Caffe it's not being used right now. So with those frameworks, it runs. If somebody's developing like their own framework and they haven't included the Intel MKL DNA library, then it wouldn't work. But with the popular ones, which I would guess 99% of the community would be using, then they can take advantage.
yeah, and I think that's the case with like any, any software stack, right? I mean, there is like a new framework out there. If you have existing tools, then maybe you can map it to that framework. But
there's more processor innovation happening in AI than I've seen in years. I mean, all this stuff with IMUs and IP things, and it's just amazing what's available out there. And trying to compete with that with a general purpose processor is a bit of a challenge, quite frankly.
So actually, I mean, I want to say that AI, I mean, is machine learning and deep learning. We don't spend enough time as Intel talking about, like, we already own the machine learning market. I mean, machine learning today runs on Xeon. And we don't spend enough time talking about it. I mean, for deep learning, sure, I mean, it's been a little coming from behind with image classification and like those type of the common workloads, which is where deep learning started with. But now, as we're exploring new workloads, we're definitely seeing that it's not just, I mean, and it's like early days for everybody, right? I mean, our own, at Intel, I mean, we have like multiple lines. We have like, Lisa was talking about that yesterday, like there's a range of AI hardware. There is ASICs that we are going after for training, for inference. There are GPUs that we are going after. So, and there is our Xeon, and there are FPGAs. So there is a range of hardware where, as you're saying, the field is exploding, and different hardware might suit different workloads. But in general, you still want to. I mean, I think a big part of so the workload. I mean, the workloads should be running on platforms to which they are best suited to. And we are like, I mean, it's this journey with DL Boost, we were able to find out that the range of workloads that we've been able to enable has been much higher than where we were before. And so every generation like that, I feel, is just going to be learning to get to that, as the field evolves.
And to add to what Neil's saying, given the rapid changes that's happening in AI, something you have to ask yourself, if you were like making hardware, is do you or if you're a customer, do you rely on one ASIC given how rapid the field changes, or do you rely more on a general purpose compute that can adapt to new workloads? For example, reinforcement learning is one workload that is gaining a lot of popularity in AI. And if you see like the MLPerf benchmark, which is a popular AI benchmark, Intel has, it's leading in reinforcement learning on Xeon. I don't think even that other competitors even run their workloads on these benchmarks. So there are workloads that today have a better affinity for Xeon, and given how fast it changes, I think relying on general purpose CPU has some benefits. ASICs, even though I somewhat dismiss them for a little bit, I do think that they have their place, and so Intel, we're also investing in developing ASICs for deep learning by developing an ASIC that has a lot of matrix multiply and capabilities.